You know that feeling, right? You plug an Ethernet cable into your laptop, those little lights start blinking, and boom, you're connected. It just works. But have you ever stopped to think about what's actually going on inside that wire? Well, today, we're going to pull back the curtain on the elegant rules of Ethernet that turn a total jumble of signals into the reliable networks we use every single day.
I mean, think about it. What's stopping your local network from becoming one giant digital traffic jam? You've got your laptop, your phone, your TV, your roommate's gaming console, all trying to talk at once in the same space. How does any message get through clearly? Well, there has to be a system, a set of rules. And that system, as you've probably guessed, is Ethernet.
And this whole system has a pretty cool origin story. See, back in the 70s at the legendary Xerox PARC, they had a very real-world problem. They'd built the world's first laser printer, which was amazing, but they needed all the computers in the building to be able to use it. A researcher named Robert Metcalfe got the job of figuring that out, and the solution he and his team came up with would eventually become the industry standard we all know and use today.
All right, so if you're going to create order from chaos, the very first problem you have to solve is identity. Right? In a room full of people talking, you need names to know who's who. Well, it's the exact same thing on a network. So how do you give every single device its own unique name? The answer is the MAC address, which stands for Media Access Control Address. And the key thing to get here is that it's a burned-in address. Think of it like a permanent serial number for your device's network card. It's this 48-bit code that the manufacturer assigns, which means that, in theory, no two network cards anywhere in the world should ever have the same one. And here's a really great way to understand why that uniqueness is so important. Imagine you're at a crowded costume party. If you yell out, "Hey, Bartholomew," and two people turn around, you've got a problem. Who gets the message? It's instant confusion. And that's exactly what happens on a network.
And we're not just talking about a little glitch. If two devices with the exact same MAC address somehow end up on the same local network, the result is, well, one Reddit user put it perfectly: mayhem. The network hardware, the switches, they get totally confused about where to send data. Messages go to the wrong place or just get dropped altogether. So yeah, unique identity is the absolute foundation for an orderly network.
Okay, so every device has a unique name. Check. That's step one. But now we need a standard way to actually send messages. You can't just shout raw data into the ether. You need a package, a kind of digital envelope that everyone agrees on how to open and read. And that package is the Ethernet frame. It really is like a digital envelope. It's got the destination MAC address, that's the to field, and the source MAC address, the from field. Right in the middle is the actual data you want to send, that's called the payload. And then stuck on the very end is something called the frame check sequence. That's a super important error check, and we'll talk about exactly how it works in just a second. Now, there's a limit to how much you can stuff inside one of these digital envelopes. The standard maximum size for that data payload is 1,500 bytes. This is what's known as the maximum transmission unit, or MTU. So if your data is bigger than that, like a big file download, it has to be chopped up into multiple frames before it can be sent out.
So we have identity, and we have a standard messaging format. But there's one more huge problem to solve. How does the device on the receiving end know that the message it got is the exact same one that was sent? What if a little bit of electrical noise or interference messed up the data while it was traveling? How do we guarantee the message is perfect?
The answer is this really clever mathematical trick called a cyclic redundancy check, or CRC. This is that frame check sequence we saw a minute ago. It's an incredibly powerful way to detect if any errors have crept into the data. Now, it's really important to note, it can't fix the errors, but it is unbelievably good at spotting them.
The best way to think about it is like a unique digital fingerprint. The sending computer runs all the data through a special math problem to create this little CRC number, the fingerprint, and it sticks it on the end of the frame. Then, when the receiver gets the frame, it performs the exact same math problem on the data it received. Then it just compares its fingerprint to the one the sender attached. If they match, perfect, the data is good. If they don't, it knows something went wrong, and it just throws the entire frame away.
So let's just put all the pieces together. What we've really been talking about are the three pillars that make Ethernet work so well: a unique identity for every device, a standardized way to package messages, and a totally foolproof way to check for errors.
And that right there is the magic of Ethernet. It's this beautiful system where these three simple, powerful ideas work together perfectly. Unique MAC addresses solve the identity problem. Standardized Ethernet frames solve the messaging problem. And that cyclic redundancy check solves the integrity problem. Altogether, they create the stable, fast, local networks that are the bedrock of our digital lives, creating real order from what would otherwise be total and complete chaos.
But all this brings us to a really interesting modern-day question. This whole system we've described is built on the idea of a permanent physical MAC address. But now, to protect our privacy from being tracked, our smartphones and laptops are starting to use randomized MAC addresses that actually change over time. So, if the very foundation of network identity is shifting from permanent to temporary, how are the networks of the future going to adapt to maintain that critical sense of order? It's a fascinating new problem for the next generation of engineers to solve.